Now, anytime you start thinking about PDEs, the other big physics idea that you really want to get comfortable with is dispersion relations. And it's nothing more than thinking about omega as a function of k, where omega is our usual frequency and k is our wave number. And this basic concept occurs pretty much anywhere in physics where we have a linear problem where we're worried about space and time. And most of the time you end up going into what we call k-space or omega space, which is also the same as going into omega or energy space. I mean momentum or energy space. And this is basically the way we do most of our experiments. You send in light with a particular frequency and wavelength, and you measure what comes out. And your omega of k, your spectrum for your system, tells you the possible responses, the natural responses. And so this is why it's such a fundamental idea. From a wave point of view, does anyone remember the definition of the phase velocity? Well, just the phase velocity. When we talk about the phase velocity, what are we talking about? Don't remember your 7e, huh? So our phase velocity is just omega over k. And if you think about it, right, we talked about the wave as being a function of kx minus omega t. Our phase is where we are in this space. And how we change our phase just depends on the ratio of omega over k. And so as I increase t, it tells me how I'm moving in x, for instance. And for simple linear waves, we literally just write omega equals v phase times k. And that works out. Now, there's another important velocity for a wave, the group velocity. And this is d omega dk. And this is going to tell us something about this omega of k, this dispersion relation. It's a very important idea. Notice for a standard linear wave, if I take d omega k, vg equals v phase. This is a case where no matter what the wavelength is, I have the same velocity. And that's a standard wave you're used to. Sound and light often behave that way. But there are lots of examples of nonlinear waves where this is not true. So for instance, I might have omega of k equal to the square root of k. This happens in some surface waves. And now the group velocity is very much not the same as the phase velocity, because the group velocity is now 1/2 1 over the square root of k. Right? That's the derivative of this. But now if I do omega over k, the phase velocity, which is omega divided by k, is just 1 over the square root of k, which does not equal the group velocity, which is 1/2 the 1 over the square root of k. So the two are different. What does this have to do with? It has to do with the behavior when we start making wave packets. And it's the idea, this is why we call it the dispersion relation. If I have a wave packet, to form this, by definition, there must be more than one frequency in here, or wavelength. And if they travel with different phase velocities, right, the phase velocity now depends on k, this wave packet will stretch or contract. It'll behave differently. It'll disperse, hence the dispersion relation. Now I can make special wave packets that are solitons, and this is the cool idea of nonlinear waves, where you can make a wave packet that stays the wave packet as it moves down. And that's a special case of a nonlinear wave. Now these are the sort of things that it's very useful. Let's see how Mathematica is doing. It's still running. Well, it's very useful to use Mathematica for, but some of these things take a long time, particularly on my laptop. So this is a file that you'll have access to in the course files. And while that keeps running, let me just kind of show you some of the things that we can look at. I can just take a regular normal wave, cosine k x minus 2t. So this is a wave. It'll have different wave numbers, but they all have the same velocity, 2 in this case. Okay? I can make a table of plots of, say, one with wave number 2 and one with wave number 3. Now, I'm going to make a table of the plots because I'm going to use list animate to make a movie of them. And this is a file I want you to go back and play with on your own. A couple things to notice. Notice this is a case where I've been explicit in the plot range, both for x and y. Why? I don't want it to change between frames. That'll mess up my movie. Right? Normally Mathematica will automatically generate the plot range. If you're automatically generating the plot range, it can shift, and then your movie looks funny as your plot range shifts. So here's my t that's being used to make the table. Here's my various plot range. This is just some text styling stuff to make the text look nice. Here's I'm plotting over x from 0 to 20. And so everything works. I would use list animate, and then I would make that movie. And what you'll see when you do this one is two waves with different wavelengths, but as they move with exactly the same velocity in lockstep. And I recommend getting used to plotting in Mathematica as you play with the PDE so you can see the different behaviors in space and time. That's why having 2D, 3D, and time plotting is very useful. Now, if I do this, and it looks like, oh no, still running. So if I do this with a square root behavior, so notice now I have kx minus square root of kt. Omega is the square root of k. So I've changed my behavior. If you look at this plot, same thing, and list animate it, you will see the two waves moving with different velocities, as they must, because I now have that behavior. And that's something fundamental in waves that we don't talk a lot about, and you've probably never visualized or seen before. Now I can take those and make a wave packet. Basically what I'm doing, in this case, because I'm using all values of k, what do I use to make my wave packet? If I want to sum over all values of k, I'm going to use a, what mathematical operation? Integral, because I'm summing my pieces. So I will have an integral over some amplitude as a function of k, cosine kx plus or minus omega of k times t dk. So this is my amplitude. It tells me how much of each wave number I have, and this is the basic wave behavior. And here's my nonlinear omega of k. This actually works even if I have a linear case, right? Even if omega of k is a constant, I'm still having the same behavior. And so I sum this up. This will give me my wave, and it's a function of space and time, because my integral is over dk. If I have discrete waves, I would just use a what? Sum. I would just use a sum and do that discrete sum. Now, one of the things I did that's often common, notice if you look at this, I've got cosine times cosine with time dependence here and space dependence here. Why don't I have cosine of kx minus omega t? What did I do? I did a trig identity. And if you look at this form, what would you call this in sort of normal wave language? A standing wave. Because you have if I fix time, I have my wave in space, and then I can oscillate time and the thing goes up and down. And a standing wave is a sum of right and left going waves. And now that I have dispersion, they'll spread out and do interesting stuff. So I ran this ahead of time. So there at t equals 1, it still looks mostly like it's Gaussian, because I started with a Gaussian amplitude. That's the e to the minus kx squared over 4. That's my Gaussian integral. Notice I'm also using n integrate, because this doesn't integrate nicely to an analytic form. So I've used n integrate to make a function, and I'm using that function to generate my plots. And that's part of what's taking so long. The integrations here are actually a bit time consuming. Now, as I move on in time, you see that there is the right and left going wave. They split. And if I just plot two of the right going waves, here it is at t equals, you can't see quite, it's 10. And here's t equals 80. So you see a couple of things, right? The general shape is changing. More wiggles are showing up because the wavelengths are separating. They're dispersing. They're going at different speeds. But there is a sense in which it's moved from here to here. I can kind of still talk about the center of my wave packet, roughly speaking. And that center of my wave packet is moving with a speed of about a half, if I just kind of arbitrarily eyeball where it is. Because here at 80, it's at about 40. So a distance of 40 over a time of 80 is a speed of about a half. Now, if I then compute my average k by integrating over my Gaussian, and then compute the group velocity by taking the derivative and plugging in the average k, I see that I should get a group velocity for the average k of about 0.47, about a half. So that group velocity tells you roughly how that group is going. Now it's a function of k, so you got to plug in some k to figure out what the wave packet's doing. And the average k, is a reasonable number to plug in. Now if my function had finished running, I could show you the whole wave packet moving. As you can see, my laptop is quite slow. So again, this is something you should run on your own. One of the reasons I'm doing the table and then list animate is once I've made the table, it doesn't have to execute it again to do the animation. It's a set of plots that I can animate. If I did something like manipulate to do this, every time you change the parameter, it's recalculating it. And each integral takes about 40 seconds to do. So it's hard to make any sort of animation out of manipulate. But here you can run it, leave it, come back and do it. Okay? Make sense? Why do we do this? The other reason we do this is, as I said, fundamentally, as we go to quantum mechanics, omega is energy, and k is momentum. So in any process where we're having an interaction between objects, if we think about it in terms of k-space, omega of k, we can get an idea of what's going on. And so we'll often use the language of, say, light interacting with a crystal. And you'll ask about things like the phonon spectrum, omega of k, or the electron spectrum, omega of k. And it's just telling you how the energy and momentum are related to each other, so that when you send in a light photon with a particular momentum and energy, and the process either conserves or does not conserve energy or momentum, always conserves momentum, but it may or may not conserve energy because it might be dissipated into other forms, you can ask what sort of things will happen. And so talking in momentum space is a much better way, because that's the space where things are conserved or not, as opposed to physical space. And there are any questions on that before I say the last bit with this? Did that kind of make sense? I wanted to give you kind of how we think about these PDEs physically. And it's really important to get comfortable with this. What are we doing in our basic linear wave equation? We are assuming e to the I kx plus or minus omega t. And we're doing our usual, what we've done before, converting derivatives into algebra. So del squareds become k squared. T squareds become omega squared. And our constants are left around. And we see that v, which is our phase velocity, is just omega over k. And that's why we called this v to begin with. The diffusion equation is a little more interesting. What am I going to turn that into? Again, let's assume e to the I kx minus omega t. What does a del squared become? K what?
Negative k squared.
Well, basically a k squared, yeah. And what does the du dt become?
T.
Minus I omega over alpha squared. We can do it that way. We got to keep track of our minus. Okay. So basically we get an omega that is going like I alpha squared k squared.
Proportional and alpha.
Okay. Oh yeah, the proportional and the alpha get a little crazy. So what we end up with when we plug things in is a u that's going to look like some u naught. It'll have some sinusoidal part in space for a given wave mode, but it will decay in time. Or grow in time and spread, depending on what you're looking at. Okay? You have to be a little careful, right? If you are looking at it as a single thing that's left, the peak decays, but the width spreads and grows. So depending which behavior you're looking at, you'll see different things. But notice a key feature of this that we immediately get to pull out, a nice physics thing. Can the power of the exponent have any units? No. And so we see here a relationship. We know the dimensions of k squared are 1 over length squared. The dimensions of time are time. And what we see here then is a relationship between length squared and time, or lengths going as the square root of time, which is our fundamental idea behind diffusion, right? Is that things go as the square root of time instead of time. And that is inherent in the dispersion relation of omega of k being k squared. Any questions on that? So we get a lot of physics out just by asking for a given equation, what's the e to the I kx minus omega t behavior? And you can see it gives insights even when it's not going to be the solution. So if I look at the Schrdinger equation, having made this transition, right? If I turn my minus del squared, I get an h squared here. I don't really know what to do with the v of x because that's kind of complicated. But on the energy side, I get an h bar omega out. And what I see is that I've got my kinetic energy term, I've got my potential energy term, and I've got the total energy. And that certainly when v of x equals 0, I have the simple case of omega k going as k squared. Notice this is not really a diffusion situation. This is a different kind of physics underlying it. It's simply the relationship between kinetic energy. It's telling me my dominant energy is kinetic energy. But if v of x is some other structure and behaves differently, I can change this omega of k behavior because I'll change how the energy is behaving as a function of momentum, perhaps with what v of x is doing.